All right, section 3.6 is the chain rule. Well, guess what? We've kind of already done it in the homework, but we're going to look at it again in greater detail. The chain rule tells you how to take the derivative of composite functions. Rates of change multiply. The derivative of the composite function at x is the derivative of the function at g of x times the derivative of g at x. So it's exactly what I showed you. You take the derivative from the outside in. See, what you need to remember is f composed with g of x is f, oh, well, it's right there underneath where I'm writing it, is f of g of x. So what we find when we get rid of the composition notation is we're taking the derivative of the outside function first, leaving the inside alone, then multiplied by the derivative of the inside. So we take derivatives from the outside to the inside. The outside function is something raised to the 9th. So if we let f of x, or f of u, be equal to u raised to the 9th, g of x is going to be 4 minus 3x. So when we apply this rule up here, we end up taking the derivative of the f function. The derivative of the f function is going to be 9 times something raised to the 8th. That something is this g of x function, 4 minus 3x. Take the derivative of the outside function, leaving the inside alone, and then we multiply this by the derivative of the inside function. What's the derivative of 4 minus 3x? Negative 3. So then we simplify this, and we get the derivative is equal to negative 27 times 4 minus 3x to the 8. So does that make more sense now when I say take the derivative from the outside in? The outside function here is something raised to the 9th. The derivative of something raised to the 9th is 9 times that thing raised to the 8th, and then you multiply by the derivative of that thing, the what's on the inside. Let's try another one. Find the derivative with respect to x of the square root of 3x squared minus 4x plus 6. It helps if you rewrite this function as 3x squared minus 4x plus 6 raised to the 1/2. When you take the derivative with respect to x of this function, you're going to get what? 1/2 times raised to the multiplied by, do you see that this right here is what's on the inside, and this happens to be the derivative of that? Maybe I'll leave those highlights there. Well, now we need to clean it up. 1/2 right here multiplied by this, which I can factor a 2 out of, is going to give me, cleaning this up, 3x minus 2 over the square root of 3x squared minus 4x plus 6. Do you see what happens? See, I have a common factor of 2 here that I could pull out that would cancel with that 1/2 out front. And that left behind 3x minus 2. Yes, sir. I took the derivative of the outside function, which was something raised to the 1/2 power. The something is what's underlined in yellow. And the derivative of something raised to the 1/2 power is 1/2 times, leave that something alone, raised to the negative 1/2. That's right, and that's why I wrote derivative over the highlight, because that'll actually show up in layers now when it prints, and you'll see that I took the derivative of the yellow. Example 3, find dy dx for y equals secant pi minus 1 over x. Might help if we rewrite this function as y equals secant times pi minus x to the negative 1 power. Trig functions are usually composite functions because we have typically in the angle part of the trig function more than just an x. So we take the derivative using the chain rule. The outside function here is the trig function. So when we take the derivative of secant is secant tangent, right? Leaving the inside alone. Times the derivative of the angle. And what's the derivative of this angle? It's going to be negative. Okay, derivative of a constant is 0. Pi is a constant. And the derivative of pi is 0. The derivative of negative x to the negative 1 is 1 x to the negative 2. So when you clean this up, it's not going to get very clean. We end up with secant, and then our angle, tangent, and then our angle, all over x squared. Because remember that x was raised to a negative power to make the negative exponent positive. Move it into the denominator. And we're done with this one. Alright, example 4. Find the derivative for f of x equals 5 sine e to the x squared. F of x equals 5 times sine of e raised to a power of x squared. We have a function inside of a function inside of a function here. What is the outermost function? Sine, the trig function. So when we take the derivative of a constant times the function is that constant times the derivative of the function. What is the derivative of sine? Leave the inside alone. Now we have to multiply by the derivative of the inside function. What is the derivative of e raised to a power? E raised to that power. But now I have to multiply by, because that power on e is a function of x, I also have to multiply by the derivative of the power here, 2x. So when I clean this up, let me see if I can figure out a way to get this here. Take the derivative of sine and you get cosine, leave this alone. And then you take the derivative right here and leave the angle alone. And then you take the derivative of the angle. Take the derivative of the outside function, leaving the inside alone, then multiply. And because we've got embedded layers here, we have functions inside of functions. This is where I said take the derivative from the outside in. Alright, so cleaning this up then, we're going to get the derivative is equal to 2x times 5 is 10x e to the x squared cosine of e to the x squared. I'm fond of these questions too. Quite fond. Example 5. I'm fond of these too. Matter of fact, I could just do 5 and it covers 4 and the product rule and a bunch of stuff. First of all, do you see that this is a product rule? For those of you who've slept since you took trig, you need to recall that secant cubed 5x is the same thing as secant of 5x quantity cubed, just so you see that that's the chain rule here. So what we're going to do is we're going to rewrite this function as y equals x squared times secant of 5x quantity cubed. Now when we take the derivative, we're going to use the product rule. And I'm assuming you remember the product rule. The derivative with respect to x of a product is first times the derivative of the second plus the second times the derivative of the first. The derivative here is the first times the derivative of the second. The derivative of this thing right here is 3 secant 5x raised to the second times, I'm still working on the derivative of this second term here. Derivative of secant is secant tangent times the derivative of the inside, which is just 5. The derivative with respect to x of secant x is secant x tangent x. That's the derivative of your trig functions. That's one that you've got to memorize because we use it a lot, especially in Cal 2. Here's the first times the derivative of the second plus the second, which is secant cubed 5x, times the derivative of the first, which is, that's the second times the derivative of the first. Cleaning this up, we have a 5 times an x squared, so this derivative is going to be 5x squared secant 5x tangent 5x, times 3. I forgot the times 3, so that's 15. 5 times 3 is 15. There's a problem with my parentheses. It needs to go right here. 3 and then it's secant, because I'm not squaring that 3. See the problem? Okay, so it's 15x squared, secant 5x, tangent 5x, secant squared 5x, plus secant cubed, well, let's do 2x first. 2x times secant cubed 5x. And I do have some common factors I can pull out. I have an x secant squared 5x that I can pull out that's in common, and that's going to leave behind 15x secant x, well, secant 5x, tangent 5x, plus 2 secant 5x. No, I can pull out a secant cubed, can't I? Because that term goes away. This is secant times secant squared is secant cubed. So that leaves behind 15x when I factor the x out, times tangent x, 5x, plus 2, and that's it. And why would I want to factor that out? Because when I set this derivative equal to 0 to find out where horizontal tangents are, I would like this thing factored as much as humanly possible. Because then I just set each factor equal to 0 and solve for x. And that wraps up the chain rule.